Hi and welcome to another video of assignment 15 of topic 3. In this assignment or in this video I'm going to do the same exercise but without the given optimized algorithm of Euclid. And so what's in it, you might ask? Well, point is that even though it's brute force and less optimized and it can't beat Euclid's algorithm in any way, it is a very nice exercise in practicing loops and ifs, and also a nice example of how to compare the speed of two algorithms with each other. Okay, so let's do this. The only thing I can do if I don't know the Euclid's algorithm is brute forcing my way out. And that means I have to take the definition to find out what I need to do. So if I need the greatest common divisor, I of course need to know what a divisor is. So first thing that I might do is, and I already again set up some input here, and as you might see or might witness already, that is I didn't use a parseInt from an IO read. I just fixed the input. This helps me to test the program. Well, of course, if I don't have actual tests, if I want to manually test the program, it helps to give it fixed input or no input through the keyboard, because that fastens the or speeds up the testing phase. Okay, so let's suppose you have an exercise where you have to sort 10 numbers. If you manually want to test this and you actually read in the numbers, let's say you have to run the program 4 to 5 times to test it and finally finish it, then you have already put in 40 to 50 numbers just doing such a small exercise of sorting 10 numbers. Okay, so it's useless doing this manual labor. We're here and getting paid to write software, not to put data in a computer. Well, back to the exercise at hand. Divisor. If you want to know what a divisor is, that's basically all numbers that divide the given number. Okay, so when there's a zero remainder, you could do this, and let's do this for, well, smallest to begin with. Okay, so I will have to check all numbers from, well, first of all, you might see that I have given 15 as the smallest and 12 as the biggest. So let's add the little if the smallest or the biggest is smaller than the smallest, which of course isn't possible, you might think, but that's a mix-up in the input, of course. And then we have to swap them. Okay, so let's have a temporary variable to save the smallest here, and then smallest can be reused to store biggest, and then biggest of course should be whatever is in temp. And that's of course nothing more than the swap trick we've seen in the first topic, the warm-up topic. So once we get past this if, we know for sure that smallest contains the smallest number and biggest contains the biggest number. Now, next up, what is a divisor? Well, we can easily print all the divisors, let's say for smallest to begin with. And for that, I will have to run over all possible divisors, starting at 1, all the way up to smallest, and check if it's a divisor. So if, and I don't know what to do here, so I'm just writing it in plain English. If I is a divisor of smallest, print I. and I can write this in JavaScript immediately. Okay. So when is I a divisor of smallest? When I check the remainder to be 0 if I divide smallest by I. Okay, so this is the definition of being a divisor. If I divide smallest by I and I have 0 remainder, then I is the divisor of smallest, and I'm going to print I. So let's see if I can do that. After the if, smallest will be 12 because they will be swapped, and I need to see all divisors here. I have a little error. Yes, I need to define I as a variable. Let's try again. There I have it. 1, 2, 3, 4, 6, and 12. And these are indeed the divisors of 12. Okay. I can do the same thing now with 15. And then start looking for the common ones, and of those common ones, the greatest ones. It would be another great exercise if you would drag arrays into this and store the divisors of one of the numbers in one array, those of the other number in another array, and then finally check both arrays to see the common ones, put that in a third array perhaps, and then find the biggest number in the third array of common divisors, and then you will have the greatest common divisor. Of course, this is endlessly dragging it along. Okay, so we're not going that way, but remember, it's a nice exercise if you would want to practice arrays as well. But here it's enough to see, and I'm going to tell you that each time you find a divisor of the smallest one, if it's a divisor of the biggest one as well, then you have found a common. So let's just check if biggest has this as a divisor as well. Because then I have a common divisor. So let's see if this gives me only the common divisors. And of course, for biggest, I would have 15, and this would turn me, well, this would turn the loop into printing 1, 3, 5, and 15 as divisors. But now I will find out if I have and which common divisors I have. Okay, so let's run it. 1 and 3, indeed. Okay. So now you might say, what if I turn it around and start at smallest, right? And go down to one, and I decrement I. So now I is going down. Then I will have found the biggest one of those common divisors first. 3, indeed. So now the only thing I have to do is, while I'm checking and I haven't found, so not found, and found of course will be false because I haven't found the biggest common divisor. Then I'm checking if I is not too small, because if I becomes 1, that's okay. If I becomes 0, I will stop. But also in the same check, I can't have found the greatest common divisor, otherwise I need to stop. Well, of course, now if I find one, it will be the first one. That's going to be the biggest one because I start at the end, right? And in this case, I can say found will be true. And now hopefully I will get only the biggest one, and that's indeed 3. Okay, here you go. Now let's see how you can speed up programs. let's come up with some good ideas. Let's up the ante and let's have some big numbers here. So let's do something like this. I really don't know, neither do I care, what these numbers might have as divisors, but they're huge, right? Let's see if this doesn't take it too far, because these are really large numbers here. So perhaps I should take it easy. Okay. Let's see what this does. 6. Okay. So let's see if this is okay indeed. If 1, 2, 3, 4, 5, 6 is divisible by 6, yes it is. And 9, 8, 7, 6, 5, 4 is divisible by 6 as well, and it is. Okay. So I'm going to trust the algorithm here to see or make sure that it's the biggest one. Let's enlarge the numbers a bit, because everything came through very fast. It takes a little longer. 9 should be the greatest common divisor between these two. Now I can just check that with my earlier example. Okay, and so let's for a moment check with these numbers if I get the same result, because this is Euclid's algorithm, remember? Let's make some room. Okay. And the other number is this one. So I'm just fixing the input now. Tests won't run anymore, but this is not what I need. Let's just double check with Euclid's algorithm if 9 is the one coming out. Indeed, so my algorithm is still okay. And now let's wonder how many steps or how many checks or how many numbers have to pass until we find this. For this, I'm going to have a number of checks. Of course, I will have 0 checks in the beginning. And each time I go to a number, I'm checking actually one number. I'm checking I to be the biggest, if even a common divisor of both numbers. So I'm going to have checks increment. So I have one more check. Each time I pass the for loop, I'm checking the next number. And I'm going to print out checks. Okay, just to see how many checks, how many numbers have been checked to find this. I can actually have my greatest common divisor put it at 1, because that's always going to be the divisor, right? And then here I can say let's assign I to GCD, and then I can print everything after the loop. So found, I'm going to make a little message, found GCD as greatest common divisor of smallest. And biggest. I'm just like making a little report here. Of course I need to use biggest, and then in some number of steps, so in checks plus steps. Okay, so I've found 9 as greatest common divisor of, well, those big numbers in some number of checks. Okay, And I'm calling a step each time he has to consider one number. Okay, let's just see how many numbers are checked with this program of ours. And well, I have to of course run. Let me get this typo first, and let's run this program now. And he says found 9 as greatest common divisor of those two big numbers. And well, let's see, 3, so 123 million steps. So that's quite a lot of steps, right? Can we do better? Well, let's for a moment focus on a smaller number here, and let's think about it. If I have, for instance, 12, or well, 60, okay, then I have 1, 2, 3, 4, 5, 6. I think these are all the divisors, right? So I will have on the other side, perhaps I'm not there yet, but on the other side I will have 6 to be 1 times 60, excuse me, 1 times 60, and that's 2 times 30, okay? And that will be 3 times 20, and that will be 4 times 15, and that will be 6 times 10, okay? So now between 6 and 10, I don't think I have any divisors anymore, right? 7 certainly not, 8 also not, and 9 also not, okay? Well, what you figure is that these divisors come in pairs. If I find 1, I have found 60, because if 1 is a divisor, then 60 divided by 1 is also a divisor. If I find 2, then 60 divided by 2 gives me 30, that's also a divisor. So I can find divisors in pairs. That means that I only have to check, well, almost half the range, you might say. But if you look at these, well, divisors start off being very close to each other, and then they start to get further apart. So this is not going to be half, but if I, let's say, have 16, then I can say that 1, 4, and 16, oh, I also need 2, sorry, 2, 4, 8, and 16 will be the divisors. And what you see is that 4 is actually in this special place, because 4 times 4 is 16. So I only have to go to the square root of 16. Okay? So I will take it to the square root of 60 to find half the divisors. Okay? And let me just quickly check what the square root of 60 is. There we go. That's 7.745. Okay. So I only have to go up until 7 point something to find all divisors. Okay. Do I need to round up or round down? Well, I can't round up, because if 7 point something times the same number equals 60, then rounding up will be over 60. It will be too great. Okay, so 7 would do. So round down. Okay. I can find divisors in pairs, right? And I have to go only up to the square root of the number. On the left hand side, they're close. On the right hand side, they're further apart. So that means if I go from the end to the beginning, as I'm doing right now, then I'm making it hard on myself. Because, well, I will have to check a lot of numbers between 60 and 30. I will have almost 30 numbers that aren't divisors, but I still have to check. Okay, so let's try and cope with this first. I will only have to go to the square root of smallest, and math has a square root. Okay, that's SQRT. So I will only start at the smallest one, its square root. Let's see if I get into trouble, because square root will be a floating point number, of course. But I don't think so, because it's just the upper border. Oh yes, I will run into problems because I'm decrementing I, okay? And I will never be allowed to be checked as a remainder division. So what I need to do here is floor it, right? There we go. And let's see if we can still get the same result. I have found 9 as a common divisor in a lot less steps. Remember, I had 123 million steps, and I'm down to 11,000 steps because of the fact that I'm starting at the square root and going down. But wait a minute, if the biggest common divisor will be on the wrong side of this, I will have a problem. This won't work anymore. Okay, I'm lucky that 9 is under the square root of both these numbers. Well, at least under the square root of the smallest number. So I can't do this. Even though I'm starting at the end, I'm not sure that I've checked both divisors. So I need to check two things. Okay. I will check, of course, I first, because I is coming from the end. And I will check the other divisor as well. So let, or const, we'll do const other divisor. But I can only know for sure that this is the divisor if my smallest actually is divisible by I. Okay. So I need to come up with another idea. Let's clean stuff up and say I'm going to have two divisors, right? So first divisor will be only if my smallest has this. Let's get this back in a moment. If I have found a divisor and they come from the end, so 60, then 30, then 20 will go down, and we'll print these, okay? Then, well, I can do this for those big numbers, so I can just, to have fun, write these, okay? Write I. And let's see what this brings us. Okay, and you can see he finds divisors, okay? Only 4 divisors. It's not uncommon for big numbers to have smaller divisors. Now I've found all divisors, right? And he's coming from behind. So 10,821, 3,800, 3,609, okay? What I need to do is, if I'm sure I have a divisor, then I can say, well, now I know that I found two divisors. First divisor being, so divisor 1 being I, actually, okay? And const divisor 2 being smallest divided by I, okay? So I'm just cleaning up shop. If I have found a divisor, then I know that this divisor is the first divisor, and the other one, the complementary divisor, is on the other side. So I'm going down. 60 gives me, as the first I, a real divisor. Okay. And then I find 60 divided by 1. 60 divided by 60. That's the second divisor being 1. Going down, okay, gives me 30 eventually. 30 being the first divisor. And then, of course, 60 divided by 30 gives me 2, the second divisor. Okay. And then I just have to check if these divisors happen to be, or at least the biggest one, happens to be also a divisor of the biggest number. So if my biggest number has a divisor called divisor, and the biggest one of those divisors will be divisor 1. Okay, so if this is 0, then I found a divisor that's also a divisor of biggest. So I can say I have found the divisor. Okay, and so I will say found is true, and the divisor will be my GCD. Okay, I also have to check the other divisor, but that's the smallest one. So if biggest divided by divisor 2 gives me a remainder of 0, and I haven't found yet 1, because if I found the biggest to be a common divisor, then there's no use in calling the smallest one the GCD. But in this case, the GCD might be that divisor, and then this is of course wrong. Okay, because if it's not divisor 1 coming from behind, I'm totally not sure that divisor 2 will be the biggest. Okay, so I have to run through it, but I know for sure if I start at 1 and I go up, then the complementary will be the bigger divisor. Okay, so let's try and make sense out of this. This is probably going wrong because I'm not sure that divisor 2 will be the GCD in any case. Okay, so we have to think about this. But at least if I found this, then I have found the GCD, and the GCD is that divisor. Okay, I could say if I haven't found it, I can always say that the GCD will be divisor 2, but it might be that I have found a bigger one, because if I'm coming with divisor 1 from behind, then divisor 2 will increase and will be even bigger. Okay, so if it's a divisor and I haven't found the greatest common divisor, because that would be the one on the right hand side, and so I found a divisor 2 to be the biggest one, and I have found and haven't found it, and finally I can say that this is going to be replacing the GCD only if divisor 2 is bigger than GCD. Okay, and of course I can collapse this into one big ant, and let's see what we have here. At any time, if I find one, because I'm going from the end of the smallest number to its beginning, and any GCD will be in the range of the smallest number. Okay, not the part between the biggest number and the smallest number. So then I will have two divisors. Divisor 1 being the one on the right hand side, and divisor 2 being the smaller one on the left hand side. What can happen if I find the biggest to be a divisor? The divisor 1 being a divisor of biggest, then I have found the greatest common divisor, and I can immediately stop. Okay, and the GCD will be divisor 1. If, however, on the right hand side I don't find a common divisor, then I have to find or I have to look to the complementary divisor, but these increase. So I cannot say I have found it, because there might be another one lurking that's coming up. Okay, so the best I can do is, if it's also a divisor of biggest, and I haven't found the biggest divisor because it has to skip in this case, and the divisor I found is bigger than the GCD, I'm going to say, well, this is the new GCD. Okay, let's run this and see what it brings us. Okay, so here we are, 11,203 steps, and it's bringing me 9 as the biggest common divisor. Okay, I could say perhaps that I'm going to multiply it by well, at least half of this number. So I might try to pull a trick. 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by 2. So I'm going to have this number, 62 million. Let's say 62 million as an extra divider in the two numbers. Okay. Hope I don't kill the whole program because of me being too aggressive here. But now I have found a very big divisor that's in both numbers. So let's see if it comes up with this. Yes, and that's of course this number divided by some common stuff, I guess. Okay, let's see if this is correct with my Euclid algorithm. So times 62 million, right? There we go. Yes, seems to be okay. And this looks okay. So I can either just going to fancy my input here. So I'm going to call this the factor, because I want to check with large divisors and small divisors. So I'm just going to put this in a variable factor. So if I use 1, I will have a very small divisor. That's 9, I guess. Okay. And if it's a real big divisor, then he will have found it as well. And he needs a lot more steps, as you can see. Why is that? Because of the fact that you're closing in from the right hand side. Okay, and this of course takes quite some time, because you'll check a lot of numbers that aren't divisors at all. So what if I just start checking again from the left hand side, because these divisors are closer to each other, and the square root of the number will be far more to the left than to the right. Okay, so if I find the close ones, I can calculate the far apart ones. So the only thing I have to do is start at 1 again, go all the way up, smaller or equal than the square root of smallest. There we go. And if I have found it, I can stop as well. This has to be incremented. And then I can basically do the same thing. But of course I have to change these two. Okay? Because now my first divisor, let's give them better names. Okay? Let's call this the small divisor, smallest divisor. Okay, and the smallest divisor will of course be I, and then the biggest divisor will be the complementary one, smallest divided by I. So now I have to check my biggest number with divisor, with the biggest divisor first. Okay. And if not, so if I haven't found a common divisor, because I'm checking the divisors of smallest and I'm finding this to be a divisor of biggest as well, since it's the biggest anyway and it's the first one, if I find it, go to the end, skip the test, because now I haven't not found it, so it will just end. In the case I don't have the biggest divisor as a common divisor, I will check the smallest divisor. Of course, only in the case I haven't found it, so it might be that in the same run I find it and I can't do this last check anymore. And of course my divisor has to be the in this case biggest divisor, right? No, smallest divisor, like this. Okay. So in the case of the smallest divisor, I can only be sure that is the biggest one after I've checked all of them. So the best I can do is each time I find a bigger one, save this one as the GCD. If I find the biggest one to be a common divisor, then it's surely the biggest one, because I'm checking from the back end to the left. Well, I'm actually starting on the left hand side going up, but the complementary ones thus gives us the biggest one going down. Let's see what this gives me. A lot more steps, of course. Okay, because that's of course the big factor. Let's compare with just a small one, 9. And he found it in a little, well, we cut a little of the steps out of it. It was 11,000 and then some, but now it's just 11,111, so that's pretty okay, I guess. Finding the smallest divisor of some number, okay? Now, what happens if I do this with Euclid's algorithm? So of course I need to do this with 1. Let's call it factor as well. Okay. Had nothing to do with factorial. Okay. So my constant factor will be in this case 1. This can be a constant as well. No, they change, so they can't be a constant. This changes, this changes, this changes, so can't put them up as consts. Voila. And I can take the same message now just to compare a Euclid's algorithm. Mind the fact that this won't work anymore if you run the tests now, okay? So I'm just taking this out just to compare both. And what I need to do is, of course, see how many. So I have to shorten these. Let's call this biggest as well. Smallest. Smallest, okay. Just to make them available in the message here. So this is going to be biggest, 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 and I need smallest as well. Smallest, smallest here, smallest there, smallest there, everywhere, voila. And this is the remainder. I'm going to write it out in full as well while I'm at it. Okay. There we go. And now, let's see what this gives us. And of course, the GCD in this case will be the smallest one. Okay, and this is remainder. Okay. and I still need checks. So checks will be how many numbers I check. So let's do checks started at 0, and let's increment checks here, and let's see if this makes a difference. And I can tell you that this is probably going to make a very huge difference. Okay, in just 2 steps he found the same result. Okay, it's not 9, it should be smallest and biggest. Oh yes, I can't count on these because I'm changing smallest and biggest. Okay, so that's too bad. I would need to remember these. What I can do is just I could copy these. So let's get back to B. This is smallest S, and now I will have S here, and this will be remainder. Let's just rewind everything to the small 1-letter names, and what I'm going to do is just save copy both numbers. So biggest being, and of course I don't know that this is the biggest one, but it doesn't matter because in the message there's no clear difference. I'm just adding the 2 numbers, this number and that number, so it doesn't matter. Let's call this but you could have the little if here that switches biggest and smallest, but it's not necessary as we have seen in the previous video of this exercise. So biggest being B and smallest being S. So I save copy them and then I can change them. Okay, but that's not a real issue then anymore, and I should have the right message now. Okay, I should see the 2 numbers. Here we go, this number and that number, in only 2 steps compared to our already optimized way of finding the same result. The brute force gives me a mind-blowing 11,000 steps instead of 2 steps. Okay, what if we take the big number? So let's do 62 million. I have to do it here as well. 62 million. We will see that this kind of blows out of scale because I have a lot more steps than 11,000. I have now 3 digits 30 million steps. Okay, let's see what happens with Euclid in this big number case. And surprisingly, it's just 2 steps. Okay, is this correct? No, this is not correct. What happened? Let me quickly see. Biggest, smallest checks. Well, this seems to be okay. Yes. Oh yes, this shouldn't be smallest, this should be S. Okay, just a wrong message here. Yes, now it's okay. So it's just a small bug we had in the IO.write. Right? But it's still 2 steps, so nothing's changed. I multiplied both numbers by 62 million, and well, to the Euclid's algorithm, it doesn't make a difference. It's easily or equally fast. Okay, so this is incredible how cool this algorithm is. Okay, be sure to go through this video a couple of times because it's hard. It's quite difficult, and I guess up to the partial exam, this is probably the hardest example of an exercise. And this wouldn't, of course, be the way to do it in the outside world because we have Euclid's algorithm. But this is a great example of how to practice ifs and fors and stuff like that. Okay, so here you go.